Okay, so new problem. Let me just read it. There are 3 circles, and basically 3 circles. They have a point P. You construct the power of point from P to each of the 3 circles twice at A1, B1, A2, B2, and A3, B3. You connect A1, B1, A2, and B2, A3, and B3, and you call the point P exceptional if the 3 lines are concurrent. So you have to show that all exceptional points, so all points P that can make A1, B1, A2, B2, and A3, B3 concurrent exists, and if it does, it lies on the same circle. So let's not consider 3 circles. Actually, it's very complicated if you consider all 3 circles. Let's consider just a single circle first, then point P. So let's have point P, right? Okay, sorry. Let's have point P here. Let's have a circle. So P to here, maybe A1, P to here. Oopsies. This A2. Oh wait, it's B1. Sorry, the naming convention is A1, B1. B1. A1 and B1 intersect at some like Q, whatever. Okay, now we have center O. OP 90 degrees. Link these two up and call this big O, because we claim that the circle formed by this is the circle that every exceptional point lies on. So the reason is actually quite simple. You notice that let's call this X. So triangle O1XA1 is similar to triangle O1A1P. Hence O1X. Let's call this 1 also, actually, because there are multiple circles. So O1X1 over O1A1 is equals to O1A1 over O1P. So O1X1 times O1P equals O1A1 squared. And O1A1 squared is nothing but R1 squared, where R1 is the radius of the first circle that we're seeing. Okay, so O1X1 and O1P, what do they mean? O1X1 is here. Wait, O1X1 is here. O1P is here. So if you realize this is just power of point O1 from purple circle, which can be written in its other form, which is O1 O squared minus R squared, where this R is not the same as R1 squared. This R is the radius of the purple circle, so it's R1 squared. So rearranging, what this means is that the power, okay, so this means, okay, this side actually means power of point O to circle 1 is R squared. So by similarity, R squared will also be O2O squared minus R2 squared, and also R squared is O3O squared minus R3 squared. So this one is power of O to circle 3. This one is power of O to circle 2. Notice that the R's on the left hand side, they are constant. So the power of O to circle 1, 2 and 3 are constant. Hence O is radical center of the 3 circles. Since the power of O to the 3 circles is independent on P, since there's just one value R here, hence any point that is distance R from O fits the criteria. Since we just want R squared, right? Any point that is distance R is basically any point on this circle. Hence we proved it that all exceptional point lie on a circle, specifically the one with center O in this case. Okay, we're done.